Hyperparameters are really important for reinforcement learning algorithms, but really developing optimization methods for them is infeasible. It's just too expensive, right? Well, no. That's what we tried to improve in our paper ARLBench, Flexible and Efficient Benchmarking for Hyperparameter Optimization and Reinforcement Learning, that's just been published in DMLR. I'm Theresa Eimer, and this was work that was done in large parts due to my great co-authors, most of all Janis Bektepe and Julian Dierkes, who led this project. So why did we even work on hyperparameter optimization for reinforcement learning? Well, if you look at papers in this area, we find that a lot of evaluation is very inconsistent. We see work using different search spaces for hyperparameters, different reinforcement learning implementations, and different environments. And all of that means that the results of these different papers really can't be compared at all. And that also means if you need a hyperparameter optimization method for a reinforcement learning algorithm, you won't know which one to pick. So, first order of business for us was to standardize this evaluation. That means what we want to evaluate is a hyperparameter optimization method. So we built an interface, a benchmark for that. This hyperparameter optimization method in green receives objectives, so it could be something like a evaluation reward, and optionally also state features, so we can go beyond black box methods in principle. And then the method selects a hyperparameter configuration to try, which is drawn from a uniform search space, so every method has the same range available. We can also run different training budgets, meaning we're compatible with partial evaluations or even dynamic configuration. All of that goes into the benchmark itself, which is in yellow. Here this AutoRL-env actually manages training, and we can train 3 different RL algorithms, PPO, DQN, and SAC. We also are compatible with a lot of different environments in principle. So, for example, we have an integration with envpool, meaning we can train standard environments like the Atari learning environment, Box2D environments. We can also go to GymNax for classic control, BRAX for locomotion, or XLand for grid worlds. And that means within this setup, we've already fixed 2 out of the 3 problems I just spoke about. We have a consistent configuration space, and now we also have consistent implementations that, due to JAX, are also really fast. But we're left with a lot of different environments it could evaluate the optimization algorithms on. So which ones do we actually pick? Well, this is something really interesting we did. We attempted to actually find a representative subset of environments that would be enough to test an optimization method, and then we can expect it to perform really well on all environments within our scope. So what was the scope? The scope of evaluation were the 3 algorithms I just talked about, PPO, DQN, SAC, and then 21 different environments from classic control, grid worlds, locomotion, and the ALE. And let's assume each of these environments is one of these shapes here. Then for each of them, we evaluated 256 Sobol sampled hyperparameter configurations across 10 seats. So that means within these 256 configurations, we try to cover the space as much as possible. And that gives us a mini landscape for each environment and a performance landscape for all environments in total. Now, to narrow down the amount of environments, what we then did is we picked a subset, for example, in this case, 2 environments, and used each of their optimization performance landscapes as inputs for a linear predictor. And this predictor's task is to predict the total landscape, for which we obviously have a ground truth as well. And now we do this for different kinds of subsets. We could, for example, choose a subset with different environments, we could choose a larger subset, or even a very small one. And then the goal is to find the subset that gives us the smallest distance between predicted and actual landscape. So, a subset which gives us performance that is directly related to this whole space of 21 environments. And actually, we don't need large subsets to do this. So here you can see the Spearman correlation of the subset we found at a given size for sizes 1 to 6. And as you can see, we move up really quickly to a very high correlation. At 6 environments, we're at a correlation of about 0.9 for all algorithms. And for example, for SAC, we're actually very, very close to optimum. So what we then did is we chose a size where we thought we had a very good trade-off between runtimes. So obviously choosing less environments decreases our total runtime, but also a good correlation to the actual true performance. And that means we ended up with 5 environments for PPO and DQN and 4 environments for SAC, which, according to our analysis, are very, very predictive of performance landscapes for the whole set of environments. And this is quite nice, because obviously this means a lot less evaluation. And it actually also holds in practice. We tested 4 different variations of optimization: random search, we used a black box optimizer in SMAC, black box optimization with hyperband, so partial evaluations, and then also population-based training, which does dynamic configuration online. And as you can see for DQN, we have the subset on the left, the full set on the right, and the curves look very similar. Obviously, the absolute normalized score will not be exactly the same, but the methods behave qualitatively almost the same on the subset as on the full set. And that's what we want to see. And what that now means is that we have a standardized setup that is also really fast. So if you look at the runtimes we would have if we would run stable baselines on all of our environments, obviously it would be really large, and we can already reduce that by using the ARLBench implementation. But we can cut it much further if we actually use the subset that we found. And with that, you can see not only will we get better evaluations in our papers because we are consistent now and we have a standardized evaluation pipeline, but we are also making this line of research a lot more accessible, such that it can also much more easily be done in small academic labs, for example. Obviously, if you look at the whole paper, there are also a lot of interesting facts about the performance of the optimizers and some of the interesting facts we found about this performance landscape. So do check out the full document. You can also find the benchmark on GitHub, and you can use it in your next project and tell us what we could improve.